Hi, this is Dr. Emenacker. In this video, we will continue our review of exponential and logarithmic functions. We're going to start this video by reviewing the properties that apply to logarithms. An important thing to keep in mind is that when you compute the logarithm of a number, the value that comes out is an exponent. When you look at these properties of logarithms, each of the properties deals with the outcome or the result of the log in the same fashion that you would deal with exponents if you were multiplying, dividing, raising to a power, whatever the case may be. As we work through these, you'll see what's going on. But keep in mind that these properties are based on the ideas of how you handle exponents on variables. The first of the properties that is listed is the property indicating that if you have two values multiplied together, you will take the log of the first one plus the log of the second one. Now this fits in with what we've seen before. If you'll recall, when we had something like x squared times x cubed, this gave us x to the fifth, which was obtained by adding the two exponents. The adding of the exponents is the equivalent of adding the log base a of m plus the log base a of n. With that in mind, let's go on to the second property. The second property says if we have a number divided by a second number, you take the log of the numerator minus the log of the denominator. This fits in exactly with the situation where, for example, we had x cubed divided by x squared, and this gave us x, where you have the exponents 3 and 2, and you take the 3 minus the 2, the exponent in the numerator, minus the exponent in the denominator, gives you the resulting exponent. Here you can see in this particular property, the log base a of m is the exponent in the numerator, minus the log base a of n is the exponent in the denominator. So we're just following through on what you've seen before. A third log property says if you have a number raised to a power, it's equivalent of factoring that power out and multiplying that power times the log of m. So essentially what this is saying is if you have something like x squared cubed, you're going to take your 2 times your 3. The log base a of m would be the exponent on the x squared 2. The b would be raising it to the power 3. The fourth property, I'll just leave these where they are. The fourth property basically says if you have a, you raise it to the first power. Any number to the first power is going to give you back the result that you started with. This value a that you get back is the value there listed in the logarithm. Following off of that, if we take a, raise it to the 0 power, okay, our base is a, raise it to the 0 power, any number raised to the 0 power gives you a result of 1, with that result being listed right there. The change of base is a useful property to keep in mind. What will wind up happening is we're going to encounter things like the log base 7 of 24. Well, in your calculator, there is no log base 7. There are two logs. There's log base 10, which is referred to as the common log, and there's log base e, which is referred to as the natural log. But there is no log base 7. And the reason for that is it's assumed that if you're working with things like this, you're familiar with this formula that's referred to as a change of base. You can take this particular log and you can convert it to a log in any other base. So we could do this as log base 10 of 24 divided by the log base 10 of 7. That's a 10, not 16. And on your calculator, if you're looking for log base 10, you will not see the base 10 displayed. It'll just be log, and it's understood to be base 10. You could use any other base you want to. So we could do the natural log of 24 over the natural log of 7. Remember, natural log is the log base e. Either of these two formulations will give you the same final answer. Okay, keep this change of base in mind. This is very, very important. If you have a problem where you have the log base a equals k, what this really says is the log base, or a, the base, raised to the k power, is going to give you the number that you get in the argument, which is going to be a to the k. And the very last of these properties that we're going to look at, and this one's important, it's going to be useful in solving for x in various situations. If you have an x that's greater than 0, the way that you can solve for x is if you have a log base a, you apply a to that, and it'll give you back x. You might say, what? So if we have something like the natural log of t equals 4, to solve for t, the inverse of natural log is e, so we would apply e to both sides. And on the left side, the natural log and the e will cancel, leaving us with t is equal to e to the 4th power. E to the 4th is something that you can compute on your calculator. Okay, this last property here is very important to keep in mind when we're working through problems. So we're going to be solving a lot of problems that involve logs, typically natural logs, but a lot of problems with logs, and the way that you solve or isolate the variable or whatever's inside of the natural log is by applying e if it's natural log, by applying 10 if it's a common log. If it's something like the log base 7, you would apply 7. Whatever the base is, you apply that to both sides. Okay, so that's how this particular property works. Each of these properties that's listed here is going to be important, so it's going to be something that you're going to need to be very familiar with. Make sure you spend some time learning these and how they apply. Let's take a look at some applications. In this first example down here, we have the log base 2 of 16 times 8. We can rewrite this using the first property. So using property number 1, this can be rewritten as the log base 2 of 16 plus the log base 2 of 8 equals. Now, if we take a look at each of these separately, the value that's going to come out of this particular log is, what power do you raise 2 to get 16? Well, 2 raised to the 4th power gives you 16. This particular log has a value of 4. In the case of the second part of this, 2 raised to the 3rd power will give you 8, so this would return a value of 3. So what this is really going to boil down to is 4 plus 3, which is 7. If you want, you could go and figure this out. Otherwise, we could do a check here to verify that this is accurate. We could do the log base 2. And what I'm going to do is I'm going to take the 16 times the 8, and 16 times 8 is 128. And the question now is, what power do we need to apply to 2 to get 128? Well, if you check, 2 raised to the 7th power is 128. So you can see this exponent that we obtained by applying the properties of logs is exactly what you will get if you work it out by hand. Okay, let's take a look at a second example here. In this second example, we're now looking at division. So this would be something like, or could be written as the log base 3 of 81, and using the second of the properties, it's going to be minus the log base 3 of 27. One of the things you may want to do as you're working these problems out in your homework, okay, and writing things down, is you may want to, as I'm doing here, above the equal sign, indicate which of these properties of logs you're applying in that situation. That way, as you come back to study them later, you'll know how you got to that answer. Okay, so let's evaluate this first one here. The question is, 3 needs to be raised to what power to get 81? Well, if you raise it to the 4th power, you'll get 81. Here, what power do we need to raise 3 to get 27? Well, this is going to be 3, and it just so happens that the first and second examples both are 4 and 3. That's not always going to be the case. But in this time, we're going to have 4 minus 3 equals 1. We can check this by actually working out the problem that we have. We have this log base 3. 81 divided by 27 is 3. Okay, so the question is, what power do we raise 3 to get 3 back? Or what power do we apply to 3 to get a resultant value of 3? And that exponent that we apply is 1. And notice you wind up with the same value for the exponent either way. In this third example, okay, so what are we going to do with this? Well, for this, there are several ways to work this. What I'm going to do in this particular case is I'm just going to use the change of base, which is property number 6. Okay. So for this, I'm going to apply property number 6, which says, I'll write this so you might be able to read it. We can take this log base 7 and apply any other base we want to. I'm going to use the natural log. And if we work this out, we have the natural log of 343 divided by the natural log of 7, and that gives us a value of 3. Okay, well, how else could we work this out? Another way to work this out would be to rewrite our original problem as the log base 7. 343 is 7 to the 3rd power. This is going to be equal to 3 times the log base 7 of 7. This evaluates to be a 1, which gives us then 3 times 1, which is 3. And notice in either case, we come up with the same value. Okay. In the first solution there, what I did, and I'm just going to go back, I'm pretty sure, yeah, it's property number 6. But in this second, or this check of it, I used property number 3 instead to evaluate that. So in some of these, there are multiple ways to go about solving them. Which way is the right way? They both work. Whichever you're more comfortable with is fine. Okay, in this next section here, we're going to look at some examples, and the idea here is to just give you some additional experience working with logs. Notice that in both cases, the base is A. But notice that you're given up here the values of logs base A. So whatever that base is, we don't know. But we are given what the values of log base A of 2 and log base A of 3 equal. This can be rewritten as the log base A of 2 times 3, because 2 times 3 equals 6, which is the same thing as the log base A of 2 plus the log base A of 3. This is the first property amongst those of logs. Okay, now if we look at the log base A of 2, notice at the top of the screen that has a value of 0.301, and the log base A of 3 listed at the top of the screen has a value of 0.477. Adding these two together gives us 0.778, and that's the final solution for this one. Okay, notice you don't need your calculator, and notice here, okay, that we've taken what was originally multiplication, 2 times 3, changed it to addition. Before calculators were available, this use of logs was extremely beneficial because it would take multiplication, turn it to addition, and as we'll see in the next problem, it would take division, turn it to subtraction. So what it does is it kind of downgrades each of the operations by one level of complexity. Okay, so let's take a look at the second one now. We have 2 divided by 3. This can be rewritten using the properties of logs as the log base A of 2 minus the log base A of 3. This is using the second of the properties of natural logs. Okay. Looking up the value for each of these, the log base A of 2 is 0.301 minus the log base A of 3 is 0.477. Okay, so let's go ahead and work out the subtraction. So we have the 0.301 minus 0.477, and that gives us a value of negative 0.176. Now, something I'm going to point out here. I know on your calculator it typically will not display this 0 on the front end. I typically write the 0 there to draw attention to the fact that there is a decimal point here. Takes a little extra time, but it's better than overlooking the decimal point and getting the whole problem wrong just because, oh crud, I forgot there was a decimal there. For this third problem, this can be rewritten as the log base A of 2 raised to the third power, because 2 cubed is 8. If we go back up and we check our properties of logs, you'll notice property number 3 right here deals with a number raised to a power. So we're going to use the third property down here to rewrite this as 3 times the log base A of 2, which is going to give us 3 times the value of the log base A of 2 is given as 0.301, which you should be able to do in your head is 0.903. So that gives you that. Okay, let's move on with logs. As I mentioned earlier in the video, there are 2 basic logs that we are going to encounter. One of those is what is referred to as a common log, and the other is the natural log. When you use the common log, or the log base 10, you're going to wind up just using the button on your calculator that says LOG, and that button that says LOG on a TI 8384 is in the first column, and it's the 4th button from the bottom. We can enter into the calculator, for example, if we're going to do a change of base here, where we have the log base 5 of 12, we could enter that in as the log of 12 divided by the log of 5. When you enter it into your calculator, it's going to look something like this, the log, and you're going to use that button, first column, 4th from the bottom, divided by the log of 5, and it'll give you a value of 1.544. Typically we'll round things off to 3 decimals, that's fine. Unless we're dealing with money, and then as we've talked about in an earlier video, round it off to 2 places. Okay, here's a second example using a change of base with a common log. I don't know that we need to go through that in any great detail, but it's a second example that you can try if you want. I want to take a look at two other items. One of these deals with graphing. If you'll recall from your algebra classes, a function and its inverse when graphed wind up being mirror images, and they're mirror images around the line y equals x. So y equals x is like this, and if I put down this line y equals x, notice that the graph of y equals 2 to the x, it's a typical exponential graph, is going to be increasing as you move to the right, is a mirror image of the equation y is equal to the log base 2 of x, log base 2 of x being the inverse of 2 to the x power. One of the things that you're going to need to be very good at doing is to determine the domain and the range for each of the functions that you're working with. It's important to know what values are legal to use and what values are not legal to use. Recall that domain is always going to reference x values. Range is always going to reference y values. Now the nice thing about having a graph is that you can look at the graph, and from that you can determine, well gosh, what are the values that we can come up with in this first case for the x values. So if we're going to look at the domain, the x values of y equals 2 to the x, we can come over to our graph and notice that the left side of this graph continues to negative infinity, so the x values continue to negative infinity, and we continue to move to the right as this function goes up. So what's going to wind up happening here is our domain is going to be the set of x values where x can be anything from negative infinity to positive infinity. Okay, so our x values can be essentially anything. This is not going to be true of the y values. Looking at that same graph, once again, we're now looking in the y direction. In other words, how far up can we go and how far down can we go. Let's first look at how far down we can go. We can never go below the x-axis, which means y will never go below 0. Now the question here is, can y reach 0? And the answer is no, because it runs asymptotic to the x-axis, so y can never reach 0. And as this graph continues to the right, it's going to infinity, so the y values can reach infinity. In this case, it's going to infinity upward, not just to the right. Let's take a look now at the domain and the range of the inverse to y equals 2 to the x. The inverse of y equals 2 to the x is going to be the log base 2 of x. That's the second of the two graphs that we have here. If we're going to look at the domain, that's going to be our x values. Be careful to keep domain and range separate. I will use the terms domain and ranges on quizzes and tests and things, and you need to know that domain applies to x and range applies to y. Okay? So the domain is the x values. If we look at the graph that we have here, notice that our graph continues down. In the y direction, it's going to negative infinity, but in the x direction, it never goes past the y-axis. In other words, the x value never becomes negative. And in fact, the x value never even reaches 0 because it's running asymptotic to that y-axis. So the x value starts just to the right of 0, and as we go to the right, the x value can go all the way to infinity. When we look at the range, when we're using this graph, we're now looking at the y values. Moving to the left, the y values can extend down to negative infinity. And as this graph moves to the right, it continues to go up, though at a slow pace. But when you've got an infinite number of values of x to use, it continues to go up and up and up. which means that the y value will eventually reach infinity as well. Okay, or move toward infinity. You can't actually reach infinity. Okay, that would mean it's a number you can get to. Okay, so be sure that you're able to compute domains and ranges. An easy way to do these, or one way to do these, is to have a graph and just look at the graph and reason out what x values and y values are appropriate. As a last example in this particular video, let's return to a problem that we did in an earlier video, where you have a town with a population of 36,000 people in the year 2010. In that same year, the primary employer moves the operation to another state, and once the company leaves, people start to gradually find jobs in other locations and move to other towns. By 2020, the population has dropped to 29,500 people. Compute the average annual decrease in population. This is the part that we did in an earlier problem, and the equation that's jotted down there for you is the equation that we obtained. Having now obtained this equation, we can go on to answer other questions. For example, the one that's posed below. In what year will the town's population fall to 26,000, assuming the rate continues as it has up to this point? So what we want to do is we want to find the value of t where we're going to have a population of 26,000. So I'm going to set the 26,000 as my population I'm interested in obtaining. Not that the town wants to continue to decrease, but just for the sake of this problem. So there's the setup. The new population that we're looking at obtaining or reaching is 26,000. What we want to do is we want to solve for t. Well, t is up here in the exponent. That might be kind of a problem. So the first thing I'm going to do is I'm going to divide both sides by this 36,000, because what I'm trying to do is to isolate to obtain t. And when I divide by this 36,000, move that up a little bit, I got the 26,000 divided by the 36,000, and that's going to give me 0.7222 equals, I'm going to save some space, 0.98 raised to the t. And the reason I save some space here is I want to apply one of the properties that we discussed in natural logs. If you'll recall, if I apply some log, and I'm going to use the natural log, I'll often use the natural log. You can use the log base 10 just as easily here. But if I apply a log, recall using property 3, this says that we can then take this exponent and move it out front. Now if I've applied the log to the right-hand side, that means I also need to apply it to the left-hand side, and this will then give me the natural log of 0.7222 equals t times the natural log of 0.98. Remember that the natural log 0.98 is a number. So what I can do is I can divide the right side by this natural log, and then I also need to divide the left side by the same value, 0.98, and this will then give me that t is equal to the natural log of 0.7222 divided by the natural log of 0.98. Okay, so on your calculator, you can plug in 0.7222, close the parentheses, divided by the natural log 0.98 equals. Now I mentioned close the parentheses. By that I mean that when you're entering it into your calculator, when you press natural log, it's going to give you natural log and open the parentheses. After you enter in this value, you need to close the parentheses before you do this division. If you don't close that parentheses, it's going to treat it all as one natural log. When you evaluate this natural log over the other natural log, you're going to wind up with a value t is equal to 16.103. This means that 16 years, or actually 16.1 years after the year 2010, the population will reach 26,000. Now, this is an estimate. This may be something that the City Council is discussing. They're saying, wait a minute, if this continues as it is, we're going to be down to 26,000 people in 16 years. It allows them to have some feel for what's going on with the situation and then to take measures to correct this. Typically, you don't want your town to continue to get smaller and smaller and smaller, or it'll dwindle away to nothing. Okay? One other point I want to make here is be careful. This is not 16 years and 1 month. Okay? This is 16 years plus 1/10 of a year. 1/10 of a year is about 1.2 months. Okay, sometimes I have seen people read off the decimal as months. This is not months. Okay, so if you're thinking that this is months, that is not the case. Okay, so the answer to this would be, when's it going to reach a population of 26,000 people? A little over 16 years. Okay, so they may want to consider taking some actions trying to attract other businesses into the area or industry into the area so that their town doesn't disappear. Okay, so this finishes up the review for exponential and logarithmic functions.